I wanted to talk to you guys about something I've really had on my mind for a while and have been thinking a lot about and reading a lot about, and wanted to share with you now and put together this PowerPoint so I can share with you. And that is, how we got to a place where so many indoor spaces have got mold and microbial growth in a way that's really problematic for people with chronic health issues like chronic inflammatory response syndrome, with environmental illness that react to microbial growth. And I have gone down the rabbit hole of looking at the evolution of building, especially in the Western world. And so this video and this presentation is really going to focus on the evolution of a kind of building that happened, starting in Western Europe and spread into the New World, which is basically building using a wooden frame and then putting other materials on top of that wooden frame. And that evolved, from Neolithic Europe, medieval Europe, through to modern times. And I wanted to kind of just put some meat on those bones of understanding how that evolution happened and what kind of materials were used in the past, how those materials changed in present day, how maybe we lost some ancestral wisdom along the way in terms of the materials we use, in terms of the way that we build. We might have unknowingly created a bit of a health crisis, which is, I think, what happened, and I'm going to share some of what I learned. Today's video and presentation are really going to focus on the kind of building, the framing, building with other materials on top of those frames, and it's also going to really focus on wall assemblies. Foundation and roofs are also important, but today we're going to focus on wall assemblies and how they might be contributing to moisture accumulation. So my first question really, when I was thinking about, water damaged buildings and the effects they have on my health is, how common is this issue? How common is water damage in buildings? And as it turns out, it's pretty darn common. And according to insurance data, it is the leading cause of property loss in North America. About 85% of buildings have had some level of water damage at some point in their past, and about half, just almost half, have got some sort of hidden dampness. So it's pretty darn ubiquitous, guys, which was my suspicion, but it has been confirmed. My next question was how does it even happen? How do we end up with moisture in the walls? And, just thinking about it before even really reading about it, it became, I was already aware that, plumbing leaks and roof leaks and large floods, that sort of thing can definitely cause issues, and we're all aware of those things. And, buildings need to be done properly to avoid those things from happening and remediated very quickly if those things do happen. But that being said, there are some less obvious ways that moisture gets into walls, which I didn't really think about. It wasn't very intuitive until I started reading about moisture management in building science. So one of the ways that it gets into walls is it's carried with air, and that's a lot of a bigger force. It's a bigger force than the other way, which is vapor diffusion, but I'll talk about carried with air first. So what happens is that all air has some level of moisture in it. We're all familiar with super dry air, not very comfortable to live in. We're all familiar with super humid air, also not that comfortable. There's a nice kind of middle ground in terms of humidity for us as human beings. That being said, warmer air has the capacity to hold a lot more moisture than colder air. So what happens is that when warm air does get into walls, when it travels through air cracks or openings in walls, it can get to a point, if it's cooler, if it's heated inside, for example, and it's cold outside, if it reaches a point of condensation, dew point within the walls, you're going to end up with moisture accumulation in the walls, carried in there by the air. And that might not seem like anything at first, but over time that really accumulates, and you can end up with liters of water inside of your walls. And that water, depending on the way the wall is constructed, it can really accumulate and not get out and cause a lot of structural issues. It can cause microbial issues. It can cause mold growth. Lots of things can happen as a result of that force of water-laden air depositing inside of walls. So that's one way. The other one is called vapor diffusion, and that's just basically warmer air, again, tends to hold more moisture than cooler air, and the pressure is from higher level of absolute humidity to lower level of absolute humidity. So that the vapor pressure, the vapor tends to move in that direction. So that's another method that moisture can get into walls. My next question really was like, well, is moisture in walls bad? And, I was like, well, of course it's bad because it's going to lead to rot. But it's actually not inherently bad. So if moisture can escape before the materials that it got wet rot, there's no harm, no foul. You're all good. There's not an issue. But if that moisture gets stuck, or if the materials remain wet for long enough, then they will rot. And it also depends on what kind of materials you use. Some are much more prone to getting rotten than others. So if you have this combination of moisture getting into walls, not getting out, and materials that are really prone to rot, you've got a disaster, a health disaster, especially for people like me who have chronic inflammatory response syndrome. So the way that we build today is something called stick frame construction, and I'm going to go through a little bit of the evolution as to how we got here. Stick frame construction is what it sounds like. This is an example of it. Basically have 2x4 sticks that create the frame, and then you add a whole bunch of materials like a vapor barrier, like insulation, a weather resistive barrier, siding, sheathing, all of the things kind of go get attached to this frame. That is the way that we build today, and I'm going to go through the evolution of how we got to this way of building, and talk about some of the materials that were used in the past, as well as the materials that we tend to use today. So way back when, in Europe, though it was used in other parts of the world as well, but I'm kind of focusing on the Western world, the developed world today. So going back to like Neolithic times, medieval Europe, back at that time, we started using a type of construction called timber frame construction. It's also known as post and beam and heavy timber framing. So this type of framing, this type of building dominated building methods for thousands of years, and it really required highly skilled carpenters and joiners. There were artisan craftspeople who would create this kind of structure. This is, classic, like old school European house. This is a photo taken in France, sort of medieval times structure here, house. So it, again, was made of a strong timber skeleton, and there was lighter infill material stuck in the spaces in between those timbers. The timber frames were really heavy wood. They were vertical and horizontal members, and sometimes they were coated in tar, and which is like sort of that classic Tudor look that you might be familiar with, the tar-coated timbers, and the whitewashed, like the lime plaster sort of white in between in the infill spaces. So this kind of building was super sturdy. Like, there was a massive load-bearing frame. There was no need for interior walls to hold the structure up. There might have been interior walls, but it wasn't necessary. Like our current modern-day construction, normally in a bigger house, you're going to need load-bearing walls in order to help hold the whole structure up. So that wasn't the case with this kind of construction. And there was no nails or metal fasteners. This was made with precision cut joints with timbers that were shaped and fitted in very specific ways. So very skilled craftspeople and artisans were involved in creating this kind of housing. This is just a diagram that kind of shows the layers of a timber frame structure. I think they might have misspelled one of the words in here actually, but in any case, you'll see there's the timber frames, sometimes coated in tar. That would be weatherproofing the tar, and then within those spaces there was something called wattle, which was woven twigs. They put wattle there, but I think it's supposed to be a double T, or maybe it's like a difference between American and British spelling or something, I'm not sure. But in any case, they had wattle, which was woven twigs that was sort of put horizontally across through those sort of rectangular spaces in between the beams. And then there was daub, a material called daub, which was clay, lime, and straw that was put in layers on top of the wattle. And then it was kind of finished with a lime plaster finish, which is that white color, sort of that you'll see in this kind of old school building in between the timbers. So this is another example of a timber frame house. This is from the 1400s. It's from Germany. This is more of that classic Tudor look kind of house. And I was really interested in knowing, you know, how did this kind of construction, this kind of housing, this kind of building do in terms of drying and potential for rot. And as it turns out, all of the materials that were used were really capable of absorbing and releasing moisture. That being said, the insulation value was really, really minimal according to modern standards. So we're talking like R1 to R1.5 per inch of insulation provided by the materials that were used. So would have been a pretty low insulation value, not very energy efficient by today's standards by any means, but certainly very breathable walls. That being said, you know, they still looked after these houses. There was upkeep needed to avoid deterioration of the walls. So what they would use a plaster, like a lime plaster or lime wash finish that was painted on and applied regularly, which would allow it to shed water, but it would still allow breathing of the wall. So it was a very specific kind of mixture that they would use, but they would need to apply that regularly to maintain. And they would also have to really make sure the cracks in the daub were repaired really promptly, so there wouldn't be any weather or water coming in. So there was maintenance required. It wasn't just like set it and forget it. They definitely needed to maintain. An interesting thing that I found out as well when I was reading about this kind of construction, you know, there's a lot of these houses out there still in Europe, these buildings out there, and there's, you know, refurbishing happening and, you know, repairing them to keep them going. And what they found out is you cannot use things like brick or cement because those materials are not breathable enough and they will cause rot in these ancient structures. So I thought that was pretty interesting. The next evolution, the next major evolution in construction happened in this kind of construction, like construction with, you know, wooden frames and other materials on top, happened in the 1800s. It was after, sort of coincided with the Industrial Revolution. It was a type of construction called balloon framing. And the Industrial Revolution created a lot of new materials, including uniform-sized lumber, like 2x4s, and cheap uniform nails as well. So these were brand new materials, never had been available before in history. This kind of framing, this kind of construction was developed in the 1830s in Chicago. And, sorry, there's a mosquito. I'm in a tent right now because I'm living outside right now. Whole other story. Try not to let it bite me. All right, focus. I'm sorry. So, yes. So 1830s in Chicago was kind of when it was developed. Again, precursor to the kind of construction we do today. So the strict frame construction. Basically, we do this kind of construction with a few little tweaks and some different materials that we use, a lot more insulation, but I'll get into that a little bit more. So the benefits of this kind of construction, it was a much quicker assembly, less skill was required, less wood was needed, so much more efficient, much more accessible to a lot more people. The reason for balloon, the name balloon was actually kind of a derogatory derogatory term created by the artisans of the time who had been doing the building in the past. You know, they were very highly skilled artisans and craftsmen, and they were like, oh, it's so light and it's so shoddily done that it's like a balloon, it'll just be carried away by the wind. Fortunately, or possibly unfortunately for people like me, who I think this was the beginning of the end of quality construction, that didn't happen. They stuck around, and we're still stuck with this kind of building today. So there was a definite shift from sort of an artisanal craft way of building to an industrialized, mechanized way of building. So that's what happened thanks to the Industrial Revolution. So this is an example of a balloon frame type of construction building. You'll see that there's very long studs, so the studs were 20, 24, or even 30 feet long, so all the way from the foundation to the roof. The studs would kind of run all the way that far up, and then they were also placed 16 inches on center, so every 16 inches you'd have sort of a 2x4, which is still a very common spacing today in our stick frame construction, which I thought was kind of interesting. These standards get set, and then sometimes they just stick around for ages. And there'd be sort of an exterior wall sheathing that was used, normally some sort of covered, the walls would be covered on the outside with like some sort of wood panel sheathing. They used ribbon boards, like horizontal strips that were nailed into the studs at each floor to support floor joists. And on the interior, they'd normally put like lath and wood lath and gypsum plaster that would be attached directly to the studs, or be attached to furring strips and then to the studs. And the middle cavity, interestingly, was normally just empty. Like there was nothing in there. It was just air, which wasn't super highly insulative, as you can imagine. Sometimes it would be filled with loose material like sawdust, shavings, and sometimes mineral wool. In later years, that was kind of an evolution of insulation that we'll get into a little bit more in a minute here. But the interesting thing also about this kind of construction is that it was extremely prone to fire. And and that was because the studs ran all the way from the floor, like the mud sill, all the way up to the rafters. The studs, like the 2x4s, ran all the way up. And then also the walls were hollow, which created sort of an air convection, a chimney effect. So if it caught fire, it lit up really, really quick. So the Chicago fire of 1871, there was a great, well-known fire in Chicago, and a big part of the reason for that was that a lot of the houses in Chicago at the time were created with this balloon framing type of construction. These days, the stick frame construction we have now, we only have 8-foot long studs. We'll have a stud bay at the top and of each floor called a top plate, and those act as fire breaks. And obviously we also have insulation. Like we're not perfect by any means. It's not super ideal in terms of even fireproofness, but it's better than it was with the balloon framing. So again, I was interested in, how did these houses perform in terms of microbial and mold growth? And well, they definitely were pretty well ventilated. Like the wall cavities being open would mean there's a lot of air movement, so not a lot of chance for rot to happen within those cavities just because of so much air movement. And the construction materials were pretty vapor permeable as well. So like the wood siding would have been breathable, the lath and plaster would have also been breathable. I mean, all of these things can rot if they get wet enough, but just the combination of the fact that they were breathable and the drying potential, it was a lot less common that these materials would rot. There were, however, risks for rot. I was talking about like the convection, the warm air rising within the cavities would create natural convection currents, and the moisture-laden air would end up at the top. And if you did have any imperfections on the exterior weatherproofing, you could end up with moisture accumulation inside of the walls and some rot happening. So it wasn't, foolproof, and certainly would have needed upkeep as well. Like the walls would have, the exterior siding would have needed to be kept quite in good repair in order to avoid moisture accumulation. So again, nothing's ever like set it and forget it, which I think we sometimes forget in modern day as well. But certainly a lot of drying potential with that kind of construction. So that brings me to stick frame construction. Sort of that's the modern evolution. That's mostly what we use these days in terms of how we build. So in the 1850s to the 1900s, builders started using shorter studs, so shorter 2x4s, 8 foot long. So at each floor, you'd have like an 8 foot long stud. They started using platform framing, so there's a platform at each building level. again, would act as a fire break. Also, we were running out of old growth trees that you would need to create such very long 2x4s, long studs. Talk a little bit about the layers that are present in modern day construction. So exactly what these are made up of is going to vary, but this is going to give you like a little bit of an idea. This image is taken from a textbook on moisture management from the Building Science Corporation. So just kind of going from left to right in terms of what we're seeing here. All the way on the left, you're going to see like a siding, so that could be wood, vinyl, aluminum. There's all kinds of different things that can be used as siding on the very outside of the building. That's like sort of the first resistant barrier to weather and wind and all of that stuff. And then inside of that, you'll normally have some sort of a water weather resistant barrier. It's normally relatively vapor permeable, but this is to stop mass water from getting in, like wind-driven rain and stuff like that, from getting into the structure here. They're using something called building paper. Inside of that, you're going to have some sort of a sheathing. These days, they often use OSB, a type of engineered wood. And inside of that, you're going to have cavity insulation. So you've got the open cavity that in the balloon framing was just air. Now we always use some sort of an insulation to create more energy efficiency, to stop heat loss or cooling loss, like cold loss, depending on if you're in a heating or cooling climate. Though this wall would be in a heating climate because of where the vapor barrier is. Inside of that, you've got the vapor barrier, the vapor diffusion retarder, and inside of that, you're going to have like your drywall and probably some sort of paint on that drywall. So that's, the general way that the wall would be constructed in modern times. This varies, and there's better and worse ways to do it, but that's kind of the general gist of the layers inside of a wall. I thought I'd talk to you a little bit about some of the materials that we do use in modern construction. One of them is OSB sheathing that is very ubiquitously used. It's used in a lot of construction. It is a type of engineered wood. It's basically wood strands that are bonded with resins, and it is quite cheap, so super cost effective. Gives good structural strength. It holds water for longer, however, and it is relatively prone to rot, so you really want to keep that stuff dry if you're going to use it. Another thing that we really commonly use, or we always pretty much use in building these days, is a vapor barrier, or a vapor diffusion retarder would be a more accurate way to describe it. But it's commonly referred to as a vapor barrier. And a really commonly used one, probably the most prevalent one out there, is called 6 mil polyethylene, or 6 mil poly. And that just means it's 0.006 inch thick, and it's a type of plastic. So it's a very thin plastic sheet that's used in building. It's really important that we install it clean on a dry surface, and that we seal it really tightly, and that there are zero penetrations. There can't be any holes, which, to be fair, it's a pretty, I've been working with it this summer a little bit in some building that we've been doing, and it is a very sturdy plastic, but it's not completely impossible to puncture it, and it does happen. Like with construction, you've got nails, you've got rebar, you've got equipment, you're on a timeline, punctures and tears can happen, and they're often not repaired. And if you do end up with tears, the issue that you have is that moisture gets in, but has a really hard time getting out because it's impermeable. So you get that air movement in, bringing moisture in, but then it's really hard for the moisture to get out in time before stuff starts rotting. So that's kind of the danger with a vapor barrier that's not perfectly installed. That there is just an image, it shows you a vapor, what am I trying to say? It's a 6 mil, it's a 6 mil poly, roll of 6 mil poly there. So that's that commonly used vapor barrier. And here, I'm going to talk next a little bit about, first I'm going to take a sip of my water. Talk a little bit about the evolution of modern insulation, because we do stick this stuff right in the center of our walls now, like everyone does. We've got, these hollow walls with this insulation inside of it. So I went down reading about it, and I wanted to share with you guys what I learned. So in the 1900s is kind of when we started realizing, hey, maybe we should put some stuff in these hollow walls. And they figured out that they could use this stuff called mineral wool. They sort of discovered how to make it, and that it had sort of good insulating properties. It's called mineral wool. In terms of insulating properties, it's an R4 per inch, which is quite a respectable amount of insulation, but even by modern standards. And it's made up of a non-metallic byproduct of iron production. So it was stuff called blast furnace slag, which is metal oxides and silicates. So that was taken and combined with molten rock to create this insulation. Normally the rocks were something like basalt, was combined with the blast furnace slag, melted, spun into fibrous strands, and then sprayed with a binder. So in my opinion, this insulation is some of the better insulation that's out there still today. It is fire resistant, it's moisture resistant, and it's super breathable, vapor permeable, breathable. So it was a pretty cool invention right at the beginning when we started creating insulation. Like, we should have stuck with that, guys. But these days, the modern evolution of it is still quite readily available. It's more expensive than the fiberglass stuff that is otherwise available, or the other stuff, the spray foam. I'll get into all that in a minute. But the rock wool insulation that's available today is just stone wool. It's a subset of mineral wool, and it's made just only from volcanic rocks, and there's none of the blast furnace slag in it. It's a really great product, rock wool. If you're looking at great insulation, I would say it's probably one of the better ones. So this here is just an image of what mineral wool insulation looks like, that rock wool. This is the modern form rock wool. So in the 1930s, we started playing with fiberglass bat insulation. They were looking at ways to make it maybe like the insulation a little more malleable, easier to work with, that sort of thing. So they figured this stuff out. So it has an R value of around 3.2, give or take. It's made up of molten and spun glass and binders and additives. It's really lightweight, it's flexible, it's also cheaper. So those are some of the reasons why it was really quite loved, or like adopted. And the downside of it is that it can trap moisture quite easily, and when it gets wet, it does lose its insulation power. So those are some of the downfalls. This is what it looks like here. Still really commonly used today. It's much more prone to trapping moisture, like I was saying, and that can cause rot. So it really relies on a properly installed vapor control layer. And it was cheaper and lighter weight, really aggressively marketed, so for whatever reason it really took over building for a long while. In the 1950s, a different type of insulation was developed. It's called vermiculite. It has an R value of around 2.4. It is made up of natural minerals that are heated to 1,000 degrees Celsius, and that causes the minerals to expand and make these porous granules that are then filled into walls. It is vapor permeable, breathable, so it can regulate moisture. It absorbs and releases moisture without rotting, so that's definitely a good thing about it. On the bad side, it has been contaminated with asbestos in the past, especially vermiculite that was coming from a mine in Libby, Montana. This is what it looks like. The other thing as well is Steve has mentioned that he has worked with it before in the past, like worked with it in an older construction build that he was renovating. He said it's a total nightmare to work with, and it tends to settle as well. And so if it's settled, it will lose its insulation property. Given the asbestos link and given all that and the not awesome insulating value, I would say just steer clear of that stuff, guys. In the 1950s, cellulose started being used, and it has an R value of 3.5. It is basically a recycled paper products, so with fire retardants added, because as you can imagine, paper would light up pretty quickly. So the good thing about it is, does it have some ability to absorb and release moisture, but as you know, paper will rot if it gets too wet, so you still really need to realize that it shouldn't be getting too wet. This is just an image of somebody blowing some cellulose insulation into an attic here. It's normally blown into walls and such. So in the 1950s and later, the fiberglass bat insulation was really widely adopted, and it's still used hugely and widely today. Most of the buildings, or a lot of the buildings that are out there, will have fiberglass bat insulation in them. And another thing that started happening in the 1950s and later was that we started using rigid foam insulation, especially as sheathing on the exterior of buildings. So this stuff, depending on what kind, there's different kind, like XPS and EPS, and there's different types of styrofoam insulation, but it will have an R value of anywhere between 3.6 to 6.8, so quite a high R value. And the really good thing about putting this as sheathing on the exterior of buildings is that it would reduce thermal bridging. So thermal bridging is just this thing that happens, this idea that, where there are studs, so where the 2x4s are in a building, you're going to have heat loss, you're going to have a transfer of heat there. And you want to try and minimize that for various reasons, for energy efficiency, to avoid condensation, all kinds of stuff. So that's a good thing. Avoiding thermal bridging is definitely good. So that was one of the reasons. The other thing is it's a water resistant barrier, so it doesn't let that mass water come in. It is also quite vapor impermeable, which means as well that if water does get trapped back in there, it's going to be hard to get out and will contribute to water damage and rot issues. So this is just what a rigid foam insulation panel kind of looks like. So then in the 1990s and 2000s, a brand new form of insulation was developed called spray foam insulation. So it's got a very high R value. It depends on what kind, again, like there's different kinds, but an R7 sort of value per inch, which is very high. And it's airtight. It will expand to fill all the nooks and crannies, so super airtight. It's also vapor tight, so it won't, it acts as a vapor barrier, really effective vapor diffusion retarder. So it's being widely adopted because it really fills those energy efficiency, passive house sort of standards that we're really after as a society today. We're trying to get these super energy efficient homes, for all kinds of good reasons. That being said, if moisture does get trapped behind the spray foam, you're going to end up with mold and rot and structural decay because that moisture isn't getting out and it's hidden, and you're that spray foam is super hard to get out of place. You spray it in, and it's there, guys. So that stuff kind of scares me for that reason. I would honestly steer clear of it. Also, there's a lot of VOCs that can come off of it during curing, so my intuition is to steer clear of it. I know that there are people with other opinions out there as well, but yeah, let me know your thoughts as well. I'm always interested to hear what others have to say and what their reading and understanding is. So yeah, I'm saying ixnay to this stuff, but that's where I'm at right now. So that's just an image of spray foam insulation here. Somebody wearing their little gas mask trying to spray foam their walls. So that kind of brings me, at the beginning I was talking about how ubiquitous water damage is in buildings, and that really brings me to this idea that we have a modern building health crisis. So modern construction is made with vapor impermeable materials that really do require perfect air tightness in order to function the way they're intended and to avoid microbial growth. airtightness and high R value insulation are really great for energy efficiency, this passive house that we're really, after these days in terms of a gold standard for building. However, if you've got imperfect airtightness and vapor impermeable materials, you end up with trapped moisture behind the walls. Trapped moisture leads to bacterial and mold growth, and all of the toxic metabolites that come with those things get into the home and get concentrated in the home because of how airtight we're making it. We're making it airtight, but not airtight enough to protect our health. So, and then by virtue of it being airtight, that just perpetuates, or relatively airtight, that just perpetuates the issue indoors. We haven't got the fresh air to dilute all that toxic stuff. And there's ways that, we can introduce more fresh air, but that's a topic for another presentation, another video. So, yeah, modern building science, like we know that this is an issue. We know that the materials we use, they should dry out before they rot. So this is just an article written by Joe Stiebrick, who's an engineer who's quite well known in the building science communities. And I'm just going to read out a quote that just kind of corroborates what I've been saying. So, moisture accumulates in the building envelope when the rate of moisture entry into a building assembly exceeds the rate of moisture removal. So it's just a really simple idea, guys. If the stuff can't dry out before it rots, you got an issue on your hands. So you gotta, allow the moisture out quicker than it's coming in, so that you don't end up with rot and decay. And we know this, and it's just somehow the memo got missed. Somehow we didn't realize. Somehow the building happened in a way that this principle just wasn't adhered to, unfortunately. Now, there is an understanding that this tends to happen, and there has been an effort with better products, better materials being created, and one of those products is smart vapor retarders. So I thought I'd spend a little bit of time talking about them. They've got a permeability of 1 to 10 perms, which is quite permeable as far as vapor retarders go. So the 6 mil poly I was talking about before, that's mostly used in construction because of how cost effective it is, and how vapor impermeable it is 0.1 perms, so more permeable than that for sure. And these retarders allow some drying to occur. They do breathe a bit, and there are even some super cool, like advanced smart retarders that will change permeability according to the humidity that is present. And so careful installation is still required, so you still need to be very careful the way that you're installing it, so you still can't let go of those standards just because it's more permeable. And another downfall is that if you're in a very cold climate, you can end up letting vapor into the walls because of that vapor diffusion I was talking about earlier in the presentation. So that can lead to condensation in the walls. So, there's got to be an understanding of the climate you're working in, and an understanding of how to install this stuff properly, given all of the conditions that you have where you're building. So, but that's the same with any kind of building. There really should be that understanding, and things should be done meticulously. The other downfall is that it can be quite a lot more expensive, this kind of smart vapor retarder. This is just an image of a smart vapor retarder called SIGA installed in a build. I'll have another sip of my water here. That brings me to this idea that I've been thinking about a lot, and I've thought about for years, actually, even before I realized that air quality and indoor air and microbial growth was driving my chronic illness. But there's this idea that there's a mismatch between modern demands and ancient biology. So in the context of building, we have these modern demands, which is high energy efficiency, highly insulated, and air and vapor impermeable membranes are used in an effort to create this high efficiency home. And housing is already prohibitively expensive. Even poorly built houses are pretty expensive. And then we compound that with higher demands in the name for healthier building, and it's even more expensive. So I'm very aware of this dilemma. I live it every day. I'm in a tent right now because I don't want to be inside. And there's a 25% of us that are genetically predisposed to being unable to clear mold and bacterial toxins. And combine that with how poorly most homes are built in terms of microbial growth. Most homes, harbor those microbes. And that really, that brings me to the conclusion that obviously, for people like me that clearly have the genetic predisposition and have the biomarkers for CIRS, I'm dealing with chronic inflammation as a result of that. But, even apart from that, I really wonder to what extent is indoor air contributing to the chronic health epidemic that we're seeing today? It's a rhetorical question. I don't really know the answer. I have my ideas and my theories, but I would love to hear you guys' thoughts as well as to, to what extent might that be a driving force. We've got food, we've got water, we've got exercise, we've got sunlight, but what about the very air that we're breathing, guys? I think it's kind of a no-brainer. I think it's got a huge impact, and we tend to think of chemicals like VOCs and pollution when we think of air quality, but what if we're missing a really, really big part of it? What if microbes and microbial metabolites is a huge part? I think that's something we should all think about a little bit more, and I wish that there was more research dollars behind looking into that, because I think it might be a big one. So I know this presentation has been really quite focused on, the evolution of building, which I find super interesting, but I know it's been a little bit of a downer in terms of oh gosh, there's a lot of bad building out there. Where are we at? And I'm not gonna lie, the situation is pretty grim out there. But that being said, I really want to work on finding solutions. I want to get this information out there, first of all. I like to give context and give some way of sort of understanding where we're at, which was the aim with this with this presentation. But I do want to look for solutions as well. So what are the solutions? Well, I think there's two. There's two different types of solutions. One is we do modern homes built really meticulous in a very meticulous way, following building science principles, using healthy, breathable materials, being in tune with what your climate is, what the humidity is, what temperature is, throughout the year. So all of this stuff can be taken into consideration, and you can really build a healthy home. And there's a whole bunch of stuff about foundations and roof assemblies as well that we didn't even really touch on today. But that's really, we can do it that way. And I actually just saw a post from Dr. Eric Dorninger. He's amazing. He's an ND with great content out there, a podcast. He's got super good information when it comes to chronic inflammatory response. Definitely give him a follow if you haven't already. I'll put the information in the notes here. I just saw this post from him. He's building a 3D concrete printed home that breathes and is water resistant, and he's building it under a tent to avoid water intrusion right from the get-go. He's using some traditional construction as well, just with really better practices, and he's sharing his journey with that, so I'm going to follow that closely. Super awesome he's doing that. And he's talking about a building revolution to fix construction practices, which is what I want to do as well. I want to start a healthy building revolution. Let's all come together and push for this. We deserve so much better when it comes to building, and it's got to be way more easily accessible than it is right now. And I wish I had the solutions, but the least I can do is share my journey and the information as I find it. So yeah, number one is meticulously built modern homes. And the other one is a return to ancient wisdom. I really think that we've lost some ancestral wisdom in terms of the way we used to build homes. Now we build in a way that we've got all of these layers, we've got all this stuff in between, there's stuff hidden in the walls, and stuff can grow, and we don't even really see it or realize it other than like a bit of a funky smell, which is like kind of hard to decipher sometimes. I'm getting better at it, but I think we really lost some ancient wisdom. And so the timber frame, the way that we built, back in Europe from Neolithic and medieval times, that was a much more breathable way of building. It's not going to fly today because it just has like no insulation value, so nobody can afford to heat that kind of a place, especially in like Manitoba where I'm at right now in the winter. But I do think that there's a lot of, ancestral wisdom that we can draw on. And we've talked already about rammed earth and firewall type of construction on this channel, and I do think that therein lies a solution. It's super simple. The only reason it's more expensive is because of how niche it is, and there aren't the skilled laborers. It's quite labor intensive, but like the material is dirt. So I think that's a really cool place to look and to try and figure out how to make that more accessible to more people. So that's kind of one of the focuses here on this channel, is like looking at rammed earth and building with earth and creating that kind of a structure and that kind of a home. But yeah, so those are the two solutions, meticulously built modern homes or return to ancient wisdom. My tendency is towards a more ancient sort of informed way of building. But neither is better than the other. Both will, I think, can work. So yeah, I'm going to continue to create educational content, and I'm going to try and focus on solutions-oriented guidance, and I want to provide insight into chronic illness and air quality. I live and breathe this stuff literally right now. It's incredibly important to me because of how pervasive air quality is on my health, and how pervasive bad indoor air quality is. So yeah, if you're enjoying this content, like, subscribe, leave a comment. I'd love to have you guys follow along and let me know your thoughts as well. I'm super interested in having a community surrounding this and talking about it all. So thanks so much.